Let's configure this fairly simple topology with 4 routers for Eigrp. We'll begin on router R1. Let's go into global configuration mode, and we'll say router Eigrp. And remember, this is an autonomous system number. I'm going to use an autonomous system number of 1 for all of the routers in this example. And now we start telling this Eigrp routing process which interfaces need to participate in Eigrp. And a way we can do that is by using the network command here in router configuration mode. We can say network, and we can specify the subnet to which an interface belongs, along with a wildcard mask, and that's going to make that interface participate in this Eigrp routing process. Let's begin with Fastethernet 0/0. It's in a subnet of 192.168.1.0. It's a 24-bit subnet mask, meaning that our wildcard mask is going to be 0.0.0.255. Next, let's take a look at Fastethernet 0/1. It's a very similar configuration. We'll say network 192.168.2.0 this time, with a wildcard mask of 0.0.0.255. Remember that you can easily figure out a wildcard mask by simply subtracting each octet in a subnet mask from 255.255.255.255. And we have one other interface we want to participate in Eigrp, and it's the loopback interface. We'll say network 10.1.1.1. And in this case, the loopback interface belongs to a network of only one IP address. Notice the 32-bit subnet mask. That means our wildcard mask is going to be 0.0.0.0. And we're done on router R1. Let's go over now to router R2 and do something similar. On router R2, let's go into global configuration mode. We'll go into router configuration mode for Eigrp Autonomous System 1. And let's say network 192.168.2.0, just like we did on R1, except this time, let's not give a mask. If we don't give a mask, then Eigrp is going to assume that we're using the classful mask. Well, since this network begins with 192 in the first octet, that means it's a Class C network, and the classful mask is a 24-bit mask, so it's automatically going to assume a wildcard mask of 0.0.0.255, so we really don't need to enter it in this case. And notice that we just formed a neighborship with router R1. And if you take a look at the serial links going down to R3 and R4, you'll notice that they both begin with 172.16. One of the subnets is 172.16.1.0/30, and the other subnet is 172.16.1.4/30. What if we gave a network statement like this? What if we said network 172.16.0.0? 172 is a Class B network. The router is going to assume a classful mask, meaning that this one network statement will make both of those interfaces participate in Eigrp. We're encompassing both interfaces with this one network statement. In fact, we could do that with our loopback interface. Let's say network, and since the IP address begins with a 10, we know it's a Class A network, which has a classful mask of 8 bits. So I can just say 10.0.0.0 and not specify a wildcard mask, and that's going to make loopback 0 participate in this Eigrp process. So you see the network statements, they don't have to be an exact match for the subnet of each of our interfaces. They just need to encompass the IP address of the interface. We're done on router R2. Let's move to router R3. On router R3, let's go into router Eigrp1 configuration mode. And again, I'll say network 172.16.0.0. I'm not going to worry about specifying a wildcard mask because this is going to encompass the serial 1/0 interface. I'll just press enter. And notice the Fastethernet 0/0 interface has an IP address of 10.10.10.1. And the loopback IP address is 10.3.3.3. What if I just said network 10.0.0.0? That would encompass both of those interfaces, the Fastethernet 0/0 and the loopback 0 interface. Oh, by the way, did you notice that we had a neighborship form with router R2 just then? We're done on router R3. Let's go to router R4, and let's use one other shortcut. We began by saying network, giving a subnet address, and giving a wildcard mask. We said if we didn't give the wildcard mask, then a classful mask would be assumed. What if we did this? Let's go into router Eigrp1 configuration mode on R4, and what if I just said network 0.0.0.0? I'm being very general here. Remember I said that the network statement just needed to encompass the IP addresses of the interfaces we want to participate in EIGRP. By giving this very general network statement, I'm encompassing all of the interfaces, the loopback interface, the serial, the Fastethernet interface. I just need that one network statement as a shortcut if I want all of my interfaces to participate in EIGRP. And it looks like it worked because I just formed a neighborship with R2 and with R3. Now that we have EIGRP configured, let's give some verification commands. And let's go to router R2. That might be the most interesting router. It has 4 interfaces, including the loopback interface, participating in EIGRP. Let's do a show IP EIGRP interfaces command and see what it tells us. It tells us about these 4 interfaces that participate in the EIGRP routing process. We can also see that we're in EIGRP Autonomous System 1. We have some counters that show up. Another command we can give is show IP EIGRP neighbors. And this is going to tell me about R1, R3, and R4 that are my neighbors. And we see off of which interfaces those neighbors are available. And if we want to see what routes EIGRP is aware of, we can say show IP EIGRP topology. And notice that EIGRP knows about all of the networks in this topology, so it looks like things are working correctly. But let me draw your attention to the network between R3 and R4. It's the 10.10.10.0/24 network. Notice that there are 2 different ways of getting there. We could go via 172.16.1.6, that's R4, or we could go via 172.16.1.2, that's R3. So it's interesting that EIGRP knows about 2 ways to get to this network. However, only one of these 2 ways becomes a candidate to be injected into the IP routing table. Let's check out the IP routing table. Let's do a show IP route command. And we see that to get to the 10.10.10.0/24 network, we're going to go via 172.16.1.6. That's R4. The IP routing table doesn't seem to know about the path via R3. Let's look at that topology information again and see if we can figure out why. Here's what I want you to notice. I want you to notice this number and this number. These numbers are the feasible distances to the 10.10.10.0/24 network. And by default, EIGRP is going to go with the least feasible distance, which in this case is going to be about 5.5 million as opposed to 10.5 million. What made the difference? Well, if you notice in the topology on screen, we've got a 512K link between R2 and R4, and we've got a 256K link between R2 and R3. So the path via R4 has a lower metric, and as a result, that's the one we choose. However, the path via R3 is a feasible successor. In other words, if R2 detected that this preferred route went down, we would not have any sort of a waiting period while we try to discover a backup route. We've got this other route standing by, ready to take over. And the reason that's true is that this second route has met the feasibility condition. And the feasibility condition says that a feasible successor route will have a reported distance, or an advertised distance, which in this case is a little over 28,000, that is less than the feasible distance of our successor route. So the question is 28,160 less than about 5.5 million? Absolutely. So that means this is a feasible successor route. And it's also interesting to note that the output of the show IP EIGRP topology command only shows us successor and feasible successor routes. We may have more routes. We could add on the all-links parameter to say, show me all of the routes that EIGRP knows about, those that are successor, feasible successor, and non-successor routes. Do we know about anything else? Well, in this case, we do not for the 10.10.10.0/24 network, but in a more complex topology, we might. So we add on the all-links parameter to see even non-successor routes. Another great verification command we can use is show IP protocols. This is going to give us a lot of information about our routing protocol. In this case, we see that our routing protocol is EIGRP, and we have Autonomous System 1 configured. We see our K values, and these are the default K values, where K1 and K3 are set to 1s, and all of the other K values are set to 0s. And if you recall that EIGRP metric formula, by having these K values set, the only 2 parameters that we really consider when calculating the metric for EIGRP are bandwidth and delay. We can see this router's router ID, and it's the IP address of our loopback interface. We see that we're routing for these networks, and we see our EIGRP neighbors that are sending us EIGRP routing updates. And we also see the administrative distance, or the believability of EIGRP. For internal EIGRP, that's what we're talking about now. It's an administrative distance of a 90. Another useful command is show IP EIGRP interfaces detail, and optionally we could specify an interface after that, but let's just look at everything. And this is going to tell us, let's scroll back up and take a look at the Fastethernet interface. This is going to tell us timers. It shows us the hello interval is the default of 5 seconds. The hold time is the default of 15 seconds. It shows us that split horizon is enabled, meaning that if we receive an advertisement for a network in on this interface, we're not going to send an advertisement for that network back out of this interface. And one other thing we want to demonstrate in this video is how we can statically specify an EIGRP neighbor. It's not done very often, but we could reduce the overhead of EIGRP messages going out to our neighbors by statically defining our neighbors instead of letting the neighbors dynamically discover one another. Let's statically configure routers R1 and R2 to know about one another. Let's go to router R1, and I'm going to go back into the router EIGRP1 configuration mode, and I'm going to say that I have a neighbor with an IP address of 192.168.2.2, and it's available out of my Fastethernet 0/1 interface. When I do that, we lose our neighborship with our neighbor, and also we would lose our neighborship with any other neighbors that were learned off of that interface. So as I go into switch SW2 on screen, if there had been another router connected to switch SW2 with which I was a neighbor, I would have lost that neighborship as well. So we need to be careful if we want to statically configure our neighbors. And notice the neighborship did not reform. I need to go issue the neighbor command on R2 as well. So let's go to R2 and let's say router EIGRP1, and we'll say neighbor, and we'll give an IP address of 192.168.2.1, and it's available off of my R2's Fastethernet 0/0 interface. And now we've statically configured our neighbors, and we see that we have a new adjacency. Let's just double check that. We'll do a show IP EIGRP neighbors command, and we see that we are a neighbor with R1, or we could give the detail keyword, and it will tell us that we are a static neighbor, that R1 was not dynamically learned, it was statically configured.